Module 6, Session 3. Session 3 will cover the following content. Learning Outcome 2.5.3. Determine the area under a curve. Learning Outcome 2.5.3. Determine the area under a curve. Let's start this learning outcome off with an activity. This activity is based on a suggestion from page 11 of your assessment guidelines. Work in groups. First, spend 5 minutes discussing how you teach the definite integral and calculation of the area under a curve. Then draw the sketch of g of x and use two methods to calculate the area under the curve, by integration and by calculating the area of the geometric shape. Compare your answers from the two methods. Lastly, take a look at page 11 of your subject guidelines and think of a similar but more complex example that you could give to your students as practical assignments. Now we will move on to the theory on calculating the area under a curve using the definite integral. This is a section that students have real difficulties with, particularly when the area is both above and below the x-axis. Students need to watch the sign very carefully in these cases. We will discuss this later on. Let's take a look at a graph of a function f of x. The area that is bounded by the curve f of x, the x-axis and the lines x equals a and x equals b is given by the definite integral from a to b of f of x with respect to x. Let's take a look at why the definite integral works to give us this area. Imagine that we try to approximate the green area by drawing some rectangles under the curve. The yellow rectangles all have the same breadth, which is equal to the same change in x value along the x-axis. This is delta x. The height of each rectangle measured at the top left-hand corner is equal to the value of the function at that point. This is y. So, the area of each rectangle is equal to the length times the breadth, that is y times delta x. We can approximate the total area by adding together the area of all of these rectangles. The green gaps at the top of the yellow rectangles show that we have underestimated the area. To fill this space and to improve our estimation, we can try making the rectangles narrower and using more rectangles. To get a very accurate area, we make the width of each rectangle infinitely small. Delta x is called dx when it is infinitely small. The number of rectangles also approaches infinity. The area of one of these infinitely small rectangles is dA. Note that when we draw a rectangle with width dx on a graph, it means that the width is approaching 0. This is impossible to show, so we enlarge it for the purposes of the diagram. We now know that the area of the infinitely small rectangles dA is y dx. So if we take the integral of both sides of this equation, it means that we are summing up the areas of all of these infinitely small rectangles from the lower limit a to the upper limit b. We end up with the following. The integral of dA equals the integral of y dx, which means that the area equals the integral of y dx. Y equals f of x, which gives us our definite integral formula. The area is equal to the integral from the lower limit a to the upper limit b for f of x with respect to x. So how do we apply the definite integral formula to find the area under a curve? Let's take a look at the steps. Step 1. We sketch the graph of the function and use a very narrow rectangle inside the area that we are attempting to calculate with the length y and the breadth dx. Step 2. Find the area of the narrow rectangle using length multiplied by breadth, which gives us y dx. Step 3. Calculate the definite integral on both sides of the equation using the upper and lower limits. And lastly, simplify your answer. Let's work through a simple example using these steps. Calculate the area bounded by the function y equals 2x plus 1, the x-axis, x equals 0 and x equals 2. Our first step is to draw the graph and choose and draw in a very narrow rectangle with the length y and the breadth dx. Step 2. We know the area of a rectangle is length times breadth, so the area of our narrow rectangle here is y dx. Thirdly, to find the area between x equals 0 and x equals 2, we take the integral on both sides from 0 to 2. We know the integral of dA is a. Therefore, the area is the integral from the lower limit 0 to the upper limit 2 for y in terms of x. Remember that y is equal to 2x plus 1. This is our original function. We substitute 2x plus 1 for y. When integrating, we are adding up the areas of all the small rectangles between 0 and 2. We find our integral 2x squared over 2 plus x and put it inside our square brackets with lower limit 0 and upper limit 2. We simplify and we find our answer is 6 units squared. So we can say that the area bounded by y equals 2x plus 1, the x-axis x equals 0 and x equals 2 is 6 units squared. A situation that students often find difficult is calculating the area when the graph crosses the x-axis. Let's look at the function in the previous example again. This time we are going to calculate the area between minus a half and minus 2. First we draw the graph. As you can see, this area lies below the x-axis. We choose a very narrow rectangle with breadth dx and length minus y because it is below the x-axis. We know that area of a rectangle is length times breadth, so the area of our narrow rectangle here is negative y dx. To find the area between minus a half and minus 2, we take the integral on both sides from negative 2 to negative a half. We know that the integral of dA is a. Therefore, the area equals a negative integral from minus 2 to minus a half for y in terms of x. Remember that y is equal to 2x plus 1. This is our original function. We substitute 2x plus 1 for y. This means that we are adding up the areas of all the small rectangles between minus 2 to minus a half. We find our integral 2x squared over 2 plus x and put it inside our square brackets with lower limit minus 2 and upper limit minus a half. We simplify and we found our answer is 2 1/4 units squared. So we can say that the area under the curve y equals 2x plus 1 between the x-axis minus a half and minus 2 is 2 1/4 units squared. As you can see from this example, when we are finding the area that is below the x-axis, the length of the small rectangle is negative y because it is taken from the axis to the graph in the negative direction. If we use the correct negative sign for y as we did here, we get a positive answer for the area. If we were to use positive y, we would get a negative area, which would make no sense. Let's watch as the lecturer goes through 2 examples of finding areas under a curve.
Calculate the area included by y is equal to negative 2 over x. That already tells me that we are having here an hyperbola. The x-axis, where x is negative 1 and x is negative 3. In other words, we need to sketch that hyperbola within those 2 values. So let's start sketching the graph first, because that is what we need to do first. That is your y-axis. This here is my x-axis, and that is your origin. Now this negative 2, it's in this quadrant, and obviously from negative 1, so I will draw x is negative 1, and then obviously 2, negative 3. I will also draw, but this one is down. And then I will just try and that is my graph. And now I can just say here, obviously on here, y is equal to negative 2 over x. Now we have got the basic graph. Now you cannot find any area without the following information. We've indicated between negative 1 and negative 3, but the next thing we need to do is to put in our representative strip. You can put it in anywhere between there. Now we need to shade the graph between negative 1 and negative 3. Right, so before, what is very important, in your graph, you must have your representative strip as well as the shaded part. And if you look at exams, you get 1 mark for your representative strip, 1 mark for the correct graph, and 1 mark for the shading. So this is very, very important. Before I can calculate now the area, I need to put something extra on the graph, because that is information that I need to calculate the area, and that is the length of the strip. And we can see that that is the length of the strip, which will be equal to y. Now I can calculate the area. In order to calculate area, rotate about the x-axis, that's how we write it. It is equal to the integral. My upper limit is -1. My lower limit is -3, because that is what they were telling us. The length of the strip, that is y, and the width of the strip, that is dx. And that is the formula for area. Now we continue by substituting. Integral -1 to -3. What is y in terms of x? You can clearly see there y is equal to -2 over x. In other words, -2 over x with respect to dx. And you people know how we've worked before. It is equal to -2 outside, because that's my constant. The integral of -1 is to -3, 1 over x dx. And now I can simplify. That is -2, my constant. And then we have dealt with this most. The integral of 1 over x, according to formula number 24, ln x. And then -1 is to -3. Now we have calculated the integral. Now we're going to apply the definite integral law. -2, very important here, square bracket, ln of upper limit, which is -1, minus ln of lower limit, which is -3. And then you close your bracket. Now comes the problem. You're going to go to your calculator and you're going to punch ln -1 and ln -3, and you're going to get an error. And then what's going to happen? You're going to punch, maybe you thought you made a mistake. No. And you're going to punch, you will always get an error, because you don't get on your calculator ln -1. In other words, we're dealing with logs here, people, and that's where your log laws comes into play now. Ln A minus ln B, what does that give you? That gives you ln A over ln B. In other words, you write those separate logs as a single log. And obviously, if you continue there, can you see what you're going to get there? -2. Very nice. Ln, can you see a negative and a negative gives you a positive? And now, please don't let that negatives John Cena you. Now you go to your calculator, and once you punch that in, then you will get a nice answer of 2,197. And because you've calculated area, area is always given in units squared. Calculate the area bounded by y is equal to 2x. That is a straight line graph with a positive gradient. Between x is equal to 2 and x is equal to negative 2. So let us sketch that graph. We'll start once again with our y, and more or less in the center here with our x, and that is our origin, and this graph will look like that. It will go through the origin in a positive direction, there as well as there, and then you can just label y is equal to 2x. That's the graph. Now it states x is 2, obviously. X is 2. More or less the same size, and then x is minus 2. And that is the graph. Y is equal to 2x between x is 2 and x is minus 2. Now, after you've sketched the graphs, then it's important to put in your representative strip for the positive part as well as your representative strip for the negative part. Then you indicate there, this is dx, and you also indicate here, this is dx. And then you obviously need to shade. This is very important. From 0 to positive 2. And you also need to shade from 0 to negative 2. Now people, let's look at the graph. You have your shaded areas, 0 to 2, 0 to negative 2. It's impossible to calculate from 2 to negative 2. I think you can all see, that means you must include areas there that are not shaded. What does that mean? You need to calculate two areas here. The area between 2 and 0, and then the area between 0 and negative 2. It's important to note that. Obviously, now, I can now indicate the length of that strip, which is y. But I'm also going to indicate, and that is the interesting part here, the length of that strip, which, because it's below 0, it is negative y. It's important to note that, because I'm going to get a positive value here because it's the upper part of 0, and I'm going to get a negative value here, but times that negative will also give me a positive, because you don't get a negative area. Please, people, it's very, very important. When you calculate and you get a negative area, then you are gerook, not the calculation. So let's calculate now the area. Area x, you can do it in ones, is equal to, right? The area, let's start with a positive one because you will get positive. Upper limit is 2, lower limit is 0. Length of the strip is y, width of the strip is dx. Now can you see something here? Minus. Can you see? Because of that minus, you put it outside the integral of what's your upper limit is 0, your lower limit is negative 2, and then obviously once again y dx. I think you all understand why I subtract, because of that minus. So this is this area, 2 to 0, minus, there's the minus, and then that area 0 to negative 2. And now you substitute. Obviously, the integral 2 is to 0, y is 2x dx, minus exactly the same thing, 0, negative 2, y is also 2x, because it's one graph, dx. I hope you all are with me. Now we're going to integrate. This here, remember you must now work it out separately, Mos. This will give me 2 is to 0. And what is this? This is 2x 2 over 2. Because it's 2, then x 1 plus 1 over 1 plus 1 minus exactly the same thing here. 2x 2 over 2 and limit 0, negative 2. Let's write this in a simpler form. What does that give you? Obviously that gives you x squared. 2 over 0 minus x squared. 0 and a negative 2. And now you're going to apply the definite integral there minus the definite integral there. What does that mean? Put it all in a bracket. Upper limit is 2 and it must be squared minus lower limit is 0 and that must also be squared. That's that one. Minus, exactly the same here. Upper limit is 0 and it must be squared minus lower limit is minus 2 and that must be squared, and you close there. You don't need the calci here because here you can see you're going to get 4 minus 0. Obviously here you're going to have 0 minus 4. In the first one you will get 4. Take note, a minus and a minus gives you a plus 4. And obviously your final area there will be equal to 8. Is that correct? No, we're dealing with areas. Areas is always indicated by units squared.
Now let's try an example in groups. Calculate the area that is bounded by the graph of a function f of x equals 3 sine 2x, the x-axis, and on the sides by 2 vertical lines x equals 0 and x equals pi. Let's watch a lecturer work through the solution to the activity.
Calculate the area that is bounded by the graph of a function f of x, the x-axis, and the side lines, which are 2 vertical lines. What we have to understand here, this question simply says that integrate. So now we have to find the integral. First thing we need to do, there are some few things we need to do in order to solve this question. First of all, we need to find integral of f of x. In this case, integral of f of x, where our f of x is 3 sine 2x. That's what we need to understand. The second thing we need to note from this question is that we have some minimum and maximum. So these are your side vertical lines. So these are the lines cutting on the x-axis. So we must note of our limits or minimum as well as maximum values. We also need to understand that we must find the x-intercept. We need to understand the concept of x-intercept. Let's start off focusing on the integral. We know that the integral of sine x is equal to integral of sine x with respect to x is equal to negative cos x. This must come handy because we're going to need it later on. And then these concepts of our limit, we need to understand that pi, so in other words, pi is also equal to 180 degrees. These are just preliminary understandings that we need to have prior to solving this question. Now, let's find our intercepts. So y-intercept is equal to, y-intercept is when the value of x is equal to 0. So we can clearly go to this function and in this case x is equal to 0. So x is equal to 0. So our y-intercept then becomes so you can find out y equals to 3 sine 2x, 2x in this case, 2 equals to 0, x equal to 0. What does it mean? It means that you have a sine of 0, which is equal to 0. So the value of y-intercept is 0. Now let's find our x-intercept. So our x-intercept, we must find when y is equal to 0. Come back to this function. So your y is equal to 0. You can take away the 3. You have that right. Therefore, 0 is equal to sine 2x. This comes very handy, but there are some conditions to it. When is this equal to 0? What does it mean? It means that you must be familiar with the general shape of a curve of a sine function. So these are your y-axis, these are your x-axis. You must understand that the general curve of sine does something like this. So when is sine x, the function of sine x, equal to 0? At 180, which is pi, at 360, and at 0. This means then that 2x is equal to 0, also is also equal to 180, as well as 2x is also equal to 360. What do we want to find? We want to find the value of x, divide throughout by x. By 2. Divide throughout by 2. This means that x-intercepts for the original, the one we want here, let's transpose them here. Our x-intercepts will be then x-intercepts are equal to, I'm going to all put them inside here, equal to 0, equal to 90, as well as equal to 360 divided by 2, which is 180. These are our x-intercepts. Now that we've found our x-intercepts, then we can furthermore go to understand the question by doing this way. We want to find the area under the curve. So we want to integrate y with respect to x. That then gives us our area with our maximum and minimum. We focused here now. That's why we found these intercepts. Where does it cut our function? So we will be looking at a maximum of 90 and 0 for the function of what? For the function of 3 sine 2x. That must also be connected. Now we focus at the following maximum of 180 connected with 90. So what is happening here now? you look at between 0 and 90, which is this one. You therefore look at between 90 and 180, which is this one, for the same function. As we have earlier on stated, that the integral of sine x dx, of course, is equal to minus cos x. It should then come as no surprise when we say that the area then becomes minus 3 sine. We're integrating, so minus 3 cos 2x. Of course, we've already integrated. We're just going to apply our limits or our constraints, as well as this now. This is minus. Why is this minus? Because in this region, your function has tend. So it goes up. We can look at this one. It goes up and stops here. This is the first limit of the first boundary. Then when it goes to the other side, it then becomes negative. Hence here we have to put a negative sign. Then we come to this one, plus. But now this has a minus. So minus, this minus, then you integrate. It's plus, minus, this current minus which exists here. Then you integrate this, which then becomes minus 3 cos 2x. Of course, between 180 degrees and 90 degrees. Then your final solution. You will see once you've substituted with that, you will have 3 over 2 minus 3 over 2. So positive times negative is negative. Negative times negative is positive, which then makes it positive 3 over 2 minus 3 over 2, close bracket. Your final answer becomes 3 plus 3, which then becomes 6 unit squared, because you want area. So your area would be 6 unit, or units, you can put a plural for that, 6 units squared. Now, we need to understand this aspect now. That's why we have preliminary drawn this for our understanding. We must understand that our function will then go here, 10 at the maximum, come and intercepts here, then it comes and intercepts here with 90. So we've done this first one, this first boundary, we've done this one. Here are our intercepts. Then it furthermore has to turn around here, then goes, turns here, comes back and stops here. Complete full period of a sine function. However, our assessment was only based on what? Was only based on having to understand the further it can stretch. It can stretch till the maximum there with our line of y here. And then the area which is covered under this curve is all of that region. So you're looking at this 3 here, focused with that 3 here. Remember, we're looking at an area, and your area is unit squared. So you cannot have a negative area now. So you're looking at this portion, maximum of 3, and then at that portion, maximum of 3. As you can see, it corresponds here. This plus this equals to 6 unit squared. So we have successfully calculated the area under a curve.
This finally brings the session, the module and topic 2 to a close. Thank you for your hard work and participation.